Okay, so here's what we were talking about last time. We took a sort of a new point of view on the substitution rule. Right, so remember the substitution rule from Calc 1, and that's typically thought of as, roughly speaking, the chain rule backwards or something, right? Which is fine. It's a good point of view. Thinking, though, of the substitution rule for integrals, taking the new point of view of it as a statement about what happens when you move a Riemann sum from one axis to another axis by way of a function. What we get is a template for how to create an extension of that idea to multivariable integrals. And so we did all that last time, talked about how, the same analogous idea, and here's what results if you find yourself in a scenario where one domain goes into some function to produce another domain, perhaps much uglier looking. Right? I mean, which one would you rather do an integral over? Right? Well, the pullback argument that we made last time turns this integral over the image domain. It pulls back into this integral over the domain on the left. Right? That's what the pullback does for us. And so said differently, if we have an integral over the undesirable image domain, the pullback allows us to compute the undesirable integral's value by doing a much easier integral over a much more desirable sort of initial domain. The big point to keep in mind is you got to make sure to stick in that stretching factor. Right, that's in some sense the only thing you have to do that isn't sort of exactly what you want to do anyway. Right? Why do you have to put in that stretching factor? Well, because you got to be honest about how big is that little piece right there. This little piece of area, I'm coloring in red, that little piece of area in the xy plane simply is not the same as du dv. It's not the same as the piece of area in the uv plane that created it. This g function stretched that all out. Right? So having stretched it out, you got to keep track of how much did it stretch to produce that little red piece of area. So that stretching factor goes in there. So don't forget your stretching factor. By the way, here's a formula for the stretching factor. It's the absolute value of the determinant of the Jacobian. Right? The various different notations and expressions for how to compute that. And off you go, pretty much. So we actually started this example last time. Let's just finish it up here. So here we have a function that relates an input domain and an output domain, you might say, just like the setup that we had on the previous page. We talked about computing its Jacobian determinant. Right, and that's just a computation. That Jacobian determinant is 4uv minus 9. And this is where we ran out of time. And, what do you do with the absolute values? It's a frustrating situation to have to deal with. I mean, tragically, look at this. That stretching factor is unavoidably absolute values. Non-negotiable. So, what do we do in this case? How do I deal with the fact that there's an absolute value of 4uv minus 9? Can I just throw that away? No. Certainly not. What if it's negative? How do I know if it's negative? That's not immediately obvious. This expression 4uv minus 9, how do you get your hands on it? The way you get your hands on it is to realize that these objects in here, this u right there, it's in the picture. It's right there. We have a u-axis on our pullback domain. Right? Likewise, this v is on your picture if there is a v-axis there, right? So we are only looking at, in this pullback domain, we're looking at, this region here. And notice on that region, several things that I can say. U, look at the picture, clearly always between 0 and 1. V, again, look at the picture, clearly always between 0 and 1. So this expression here, on the region that I care about it, namely on my new pullback domain, S, where I'm doing this new integral. On that region, this expression couldn't possibly be any bigger than negative 5. That's the highest it could possibly be. More to the point, it's always negative. In this case, right, looking at the example. For all values in that square, this expression inside the absolute values that we're looking at is always negative. And because that's always negative, the absolute value of it is the negative of that thing. That's how absolute values of negative numbers work, right? And so there, we've dealt with our absolute values, and now we can proceed along. Everybody on board? Any questions? Okay. Do be careful with that last part. It's a very common mistake for students to kind of just inadvertently forget their absolute values, or to just kind of clerical error, miscopy. Oh, I forgot about that, right? And it makes a big difference. So you got to be careful about it, think it through, and make sure that it's clear what your argument is. Okay. All right. So the integral we rewrite as follows. So on our domain R, on which we're interested in this integral, we can rewrite everything in there now in terms of U's and V's. Let's see here. I'm going to need some space. I'm going to have to zoom out one notch here. So what do we do with the X's and Y's? What is that X? How do we write that in terms of U's and V's? Okay, don't forget your stretching factor tells you your formula for X, right? X is one of the output variables. There it is on our picture. It's one of the output variables for this G function. So the G function tells you what X is in terms of U and V. And you just plug that in. Straight plug in. Likewise, what do you do with all these Y's that you might have on the left side, or in your integral that you're trying to get rid of? Well, Y, again, is told to us. So you just plug that in. All right. So again, we already knew that, right? So what we had in our formula for how to do change of variables was that X and Y are functions of U and V. What we did on the previous page is just literally plug that in. Okay. What about our dx dy? What is dx dy? Well, don't forget dx dy is stretching factor times du dv, and we computed the stretching factor previously. Made our absolute values argument, so let's plug that in, and lo and behold, we have now this original integral that we don't like because the domain is highly curvy and cornery, right? Really undesirable domain, and we've now pulled that back. Now we have a new integral over a lovely domain, a rectangle. It's zeros and ones are the bounds, right? Easy iterated integral, and there's your new integral to compute. Now, do notice, the integrand got a little weirder, right? That's true, and that's a downside. But it got a little weirder, but it also didn't get all that bad. It's still a polynomial. Much more to the point, our domain is now much more tolerable. That's really the big point. And this is where the analogy breaks down between the single variable case and the multivariable case. When we do single variable substitution rule, okay, the single variable version of change of variables, our motivation is usually the integrand. We want to change our integrand. We don't like the integrand is always the challenge. The bounds are a bore. That's just the numbers you plug in at the end. That's the most who cares aspect of the substitution rule. It's just plug in some numbers, right? The motivation on substitutions in single variable is to make that integrand easier to deal with. It's kind of the opposite in the multivariable case. Most of the time we're doing a change of variables because we don't like our domain. And the integrand, okay, whatever. Well, I can deal. I can deal with an integrand. I've got integration techniques, right? But this domain is what's killing me and what I'm trying to make easier. Was there a hand somewhere a minute ago? I thought, yeah.
So, how do you get to decide what x is equal to?
Oh, yeah. Now, where the change of variables function comes from? Yeah. So that's a great question. So he asks, suppose you're just given. I want to compute this integral, and somebody draws a picture of this domain for you, and suppose that isn't given. Yeah, what do you do? And that makes it a really hard problem. right? So I'm going to show you some examples where, in certain situations you can figure out what your change of variables function ought to be. There are certain change of variables functions that are just routinely useful. We're going to spend a bunch of time talking about those a little bit later. In fact, starting today, hopefully, fingers crossed. But generically, yeah, it's a hard question figuring out what the change of variables function should be, and sometimes it's just, there's no good choice. It's not clear how to decide that choice. Yeah. So in this class, either it will be something that you can deduce by clever observations along the lines of what I'm going to show you in the next several pages, or we'll give it to you, or there's got to be some sort of I am not a monster, right? So I will. There's got to be some reasonable foot in the door in whatever problem we give you. Yeah, but it's a great question. Yeah. Okay. All right, moving along. So here's a version where you actually can identify your own change of variables function. So the question says we want to look at an integral on this domain. It's a square with those corners. Right. How are we going to do an integral over that square? Well, again, just for sort of dramatic effect, let me point out how much of a bummer this would be if I took a section 14.3 approach to this. If I slice, my y slices on the outside, well, I'm going to hit that corner, and then I'm going to hit that corner before I finish. So I'm going to have three separate integrals. And if I slice the other way, it's almost just as bad, right? We start there, slice, 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 hit that corner, slice, 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 hit that corner, slice, slice. Again, three pieces. So we don't want to do this the old-fashioned way. That's, right? So how do we proceed? What do we do about that? The observation to make here is that rectangle is a rotation of this rectangle, which I like much better. Don't we? Everyone loves that D rectangle a lot better. It's all lined up with the axes, 0 to 2, 0 to 2, super nice bounds. Oh, fantastic. Can I think of some function that will turn that yellow square into this green square? And I appeal to your geometric intuition, and it's going to be a rotation. If I just rotate that, so that's what this T change of variables function is going to be. It's just rotate it around the origin counterclockwise by some amount. You're going to have to do a little bit of geometry. Think about where these points are located. Right, flashback to high school trig. Yeah, think it through. Not hard to persuade yourself that angle is pi over 6. Okay, and by the way, yet another opportune reminder. Make sure you're really good at high school trig. It comes up. It's unavoidable. The world's full of circles, right? And that's what makes trig show up. So make sure you're highly up and proficient and fluent with all your trig stuff. Okay. Okay, so rotating by an angle of pi over 6. Now notice at the start of the question here, I know that y'all don't know, coming into Math 212, a generic formula for how to perform a rotation of a certain angle around the origin. So that's given, you'll notice here. Here's the generic formula for how to rotate a point u comma v theta counterclockwise around the origin. Nice little formula. Where does that formula come from? We're not going to cover in this class. We don't quite have the necessary tools. Well, we don't quite have the ideal tools to be able to figure that out. And if you all take Math 216, those of you who are Pratt students are definitely going to see this in 216. But if you take Math 216, we're going to introduce an idea called a linear transformation that crushes this. Right. So this is an easy example of of a linear transformation, and we can derive that formula. So take that class if you're curious. Okay. That said, let's see here. Now we know the angle is pi over 6. Plug in that pi over 6 for this angle, and our function becomes that. And there's our change of variables function. Explicit formula. And now we're all set, right? We've got our change of variables function. We see what the pullback domain is. And all we got to do is plug and chug and compute our stretching factor, plug in for our variables, and celebrate the fact that we now have a brand new, much easier integral to work out. So some details. Let's go ahead and do that. Taking these formulas for x and y, computing the appropriate partials, taking the determinant, taking the absolute value. By the way, I'm yada yada yada-ing quite a few details in there. Make sure that you remember the formula for the Jacobian matrix. Make sure that you can actually compute determinants. Make sure you remember the values of the trig functions. A lot of little micro details that go into this thing that I'm skipping over. Make sure you can do that. And now we end up with our Jacobian determinant being 1. It seems like a lot of long ways to go for such a simple answer. Let me plausibility argument that for you. Don't forget what this thing is. This is a stretching factor. Geometrically, it says how much does our change of variables function stretch areas. So now I appeal to you geometrically. If you rotate something, it doesn't change the area of it. So we better get 1, right? Clearly that should have been the answer, right? So that's good news. By the way, policy is in situations, always think about the purpose of a question that's on an exam, right? And so, on a Math 212 exam that's clearly about change of variables, I want to see the calculation, right? And in some other context, where the question's mostly about something else, maybe you might make the case that, I'm just going to make a geometry argument and argue that rotations don't stretch areas. But think about the context. If you're not entirely sure, come up and ask me during the exam before you choose to, not explain what might be a very important part of the problem. Okay. So plugging in that stretching factor, remember the purpose of a stretching factor is that's what you multiply by du dv to get dx dy. We just computed that stretching factor, stick that in there. And what do you do with the x's and y's? Well, don't forget x is given by the change of variables formula. Right, so you got to stick that into there. And y is given by the change of variables formula. So you got to stick that into there. So there's a certain amount of algebra that's going to go into multiplying all that out and collecting terms. Turns out some of the terms cancel. Writing it all down. Anyway, nice punchline. As it turns out, this integrand of x squared plus y squared simplifies through all that effort to just u squared plus v squared. So every so often you get lucky. Okay, everybody on board? Okay. Here's another situation where we're actually going to be able to come up with our own change of variables function. I have to lead into it with an observation, and that is, let me remind you, we already know that if you have a function where x and y are functions of u and v, then there's our formula for our stretching factor and how it plays, right, what it does. The stretching factor is what you multiply by du dv to get dx dy. Okay. There's nothing magic about those variables, right? Input variables do not have to, by law, be called u and v, right? Output variables do not have to, by law, be called x and y. So let's look at this same picture. Let's imagine reversing this function, just solving for u and v as functions of x and y. That's just algebra. It might be inconvenient algebra. Well, let's say that can be done, the invertible function. If you think of u and v as functions of x and y, here's what the stretching factor says. The stretching factor is what you multiply by the input differential of area to get the output differential of area. Right, so when you invert your stretching function, when you go backwards, the stretching factor just kind of goes the other way. And notice, right, If x and y are functions of u and v, the stretching factor is partial xy, partial uv. It's outputs partial with respect to inputs. If you're going the other way, it's still outputs partial with respect to inputs, but now u and v are the outputs. X and y are the inputs. Okay. Clever observation then is to say, okay, well, let's take that formula for du dv, stick it into there, and what you get is that is equal to that, which means that those two stretching factors cancel, and therefore those two stretching factors are reciprocals of each other. Here's an easy, intuitive way to think about that. To whatever extent pushing to the right stretches things, if you push back the other way, however much you stretched, well, that's how much you squish. Right? You're returning back to just where you had been. Stretches combined with squishes to get you back to where you hadn't done anything at all. So, highly plausible result. Now, resist the temptation to say, oh, well, clearly this is true because that's how fractions work. That's not a good argument. This is not true because of how fractions work. Now, let me emphasize, why I resist that argument. That's not a valid argument because these are not fractions. They aren't. Right? Look back at the definition of these stretching factors. The definition of this thing is it's a determinant. You can see it right there. It's not a fraction, it's a determinant. Right? Note the conspicuous absence of any definition of what that thing is on its own. That's not a thing on its own. Right? This is not a thing on its own. Right? So the fact, in fact, it's a little suspicious. This, having chosen, I've got this determinant over here, and the choice of deciding that, that determinant, I think I'd like to use a fraction to represent that. That should have been something we should have gotten a little upset about at the time, because why would I use a notation suggestive of the idea that this is a fraction when it's not a fraction? Right? So anyway, it's not a fraction. Going back over here to where we were, you cannot argue that this is true because that's how fractions work, because these are not fractions. All right. So I will say this, though, that even though this does not follow from an argument that these are fractions, I will point out that a nice perk of concluding this result is that now I can take advantage of the fact that I know that they behave like fractions. They aren't fractions. Definitely not fractions. They're determinants. Determinants are not fractions. But gosh, it behaves just like fractions, and that's ultra handy. Okay. All right, so this is going to come up in this argument here. Let's consider the following question, which looks very, very manufactured and arbitrary, but it's not. I'll say a few more words about that. Suppose we're doing an integral on this domain here. That domain being defined by these curves and these curves. Right, there's four curves, and the way I've got those curves drawn, you can see how they intersect, and then they're going to partition off a little region there that I have in purple. That's my R. And suppose you want to do a double integral over that region. By the way, let me tell you a context where something very, very, very similar to this comes up, and it's thermodynamics. So in my, again, long ago past life as a second major in physics, I had to take a thermodynamics class, and there is a very important calculation relating to how the Carnot cycle works. And if those of you who are engineers will eventually have to take a thermo class of some sort, I'm sure, and you'll see something along these lines. And a picture very much like this is the picture that's relevant to that calculation in relation to the Carnot cycle. So it's a very big deal in thermo. So anyway. The equations aren't exactly this, but they're very, very similar to this. Okay, so with that domain being defined, how would I do this integral? Which, again, this is an important integral in that engineering calculation. Okay. Well, again, with the corners, right? I mean, the slicing, you're going to slice through those corners kind of no matter, pardon the pun, no matter how you slice it. Right? So, on the other hand, I'm going to generate now for you a related change of variables function. And here's the really clever idea. The function is basically given to me. I'm going to define u to be xy, namely this thing here, that defines those two curves that are part of my domain's boundary. And then I'm going to let v be xy squared, namely these two functions that are central to how I define the other two edges of this domain. Right? Now, I'm choosing to do that. I don't have to do that, but those equations were given, and I'm going to make this choice, and we're going to see now why that's a really useful choice. So now I can look at these equations. The equation xy equals a constant over here, xy equals a constant, gives you a couple of hyperbolas. Over here in the UV plane, given that xy is u, the equation xy equals a constant is just the equation u equals a constant, and that's a couple of straight lines. Right, so you make that choice, u equals xy, and wow, I just straightened out my domain, yeah.
So if the two curves are the exact same.
Yeah, that's right. I'm capitalizing on the fact that these four curves kind of pair up in this nice way. And you're quite right if that's not the case. If it's just four random unrelated curves, then this doesn't work. Yeah, totally. So this is not an always thing. This is a sometimes thing. Likewise, these two curves here are, curvy in the xy plane, but they are straight lines in the UV plane. And so even though my original domain is undesirable, my new pullback domain, color choice. Okay, I'll use blue. My new pullback domain is a rectangle. Complaint. The change of variables functions go in the wrong way. Right? If I want to use change of variables, don't I need to know x and y as functions of u and v? I don't have x and y as functions of u and v. This is going backwards. Yeah, I guess that's true. Right? Now, in this case, I will point out that you look at this function. You could actually invert this function. You can solve without terribly much trouble. You can solve for x and y in terms of u and v. That's not what I want to do here. I want to show you how to avoid that effort. Right? In other words, let's stick with the function that is that comes at me most naturally. Most naturally, it comes at me going that way because that's what I was given. Right? Sticking with it going that way, notice I can compute directly partial uv, partial xy. U and v are functions of x and y. I can take those partials, assemble, take a determinant. Right? That's not that bad. That's just no big deal. And then using the result we started with at the top of the page here, when you switch directions, you just take a reciprocal of the determinant of the stretching factor. Said differently, these things that look like fractions behave like fractions. Right? If partial uv, partial xy is that, then the stretching factor that I need going the other direction, partial xy, partial uv, is just the reciprocal. And off you go. Everybody happy with that? That's a pretty cool idea. So don't feel the need to do, algebraic hero move of I'm going to take this thing and I'm going to invert this multivariable function and solve for x and y as functions of u and v. Again, it's pretty doable here, but you could certainly imagine some wacky scenario where there's like cubics involved or something like that, where you just wouldn't be able to solve. You wouldn't be able to invert that function. You don't need to invert that function you can just make this reciprocal argument like we did here. Yeah, real quick. Yeah.
You remove the absolute value because x and y is always equal.
Yeah, that's right. That's right. So the thing that we were given, good point, over here on our original domain, easy to notice that x is always positive and y is always positive, therefore that's always positive. Totally. Yeah. Okay, now there's a couple of little algebraic annoyances that come up this way. Don't forget, we're doing a pullback. Our pullback is still going that way. So I'd still like to be able to rewrite x's and y's in terms of u's and v's, and notice that this is not in terms of u and v. So I've got to figure out how to rewrite that in terms of u and v. Also, whatever our original integrand is going to have x's and y's in it. It was an xy integral. How do I rewrite that in terms of u and v? I don't have formulas for x and y in terms of u and v. So you've got a little bit of an algebra problem after you write down the change of variables formula. And that's, this is going to happen. Observation, you don't have to do those separately. You don't have to figure out how to write that in terms of u's and v's and then separately write that in terms of u's and v's. A lot of students do that. A lot of students are like, we got to do these in pieces. But notice, what you're really interested in here is this product. That product, you might get lucky. It might simplify nicely like it did here, right? In which case, this is all you really need to figure out how to rewrite in terms of u's and v's. And we got lucky. You don't always get lucky. But in this case, we got lucky. XY is exactly u. Right there staring at us in the face, and so every so often you get like, oh, did I write that wrong? XY. Okay, but this should be a U, not a V. I better do that in the pencil. Typo. XY is U. That was one of our functions. Okay, and if you don't get lucky, then you can play algebraic games. So very quickly, and I don't want to spend a lot of time on the following, but if we hadn't gotten lucky, if you find yourself with this expression in terms of x and y, where maybe m and n are uglier numbers, and you want to figure out how to write that in terms of u and v, given that, well, we know that u is that function of x and y, and v is this function of x and y, you could reasonably ask the question, how is that purple thing going to be related to that green thing and that yellow thing? And you can make a speculation. It won't always be powers, right? But here we got lucky, and the expression we're interested in is powers of x and y. The thing we want to rewrite in terms of are both powers of x and y. And how would I take powers of x and y and turn them into other powers of x and y? Plausible guess would be that, maybe this group of powers is a collection of products of powers of the things that are products and powers. It seems like a reasonable guess, right? And then you can work out the algebra, play the appropriate games, and notice that we simply need for that to be true and for that to be true. And you've got a little system of equations, and you can solve for the A and B that you need to make that work. So anyway, algebraic, it won't always look like this, but this is something kind of along these lines would be what you would try. I can't give you an algorithm that'll always work, but this is a something to try to mimic if you don't get lucky like we did here. Okay, what about in 3 dimensions? Right, so we talked about two-dimensional change of variables. Look at our original picture here. Here he is. We're presuming that our change of variables here was from 2 dimensions to 2 dimensions. So we had initially a 2-dimensional domain that we didn't like. We wanted to pull back to a 2-dimensional domain that we do like. Everything in this whole discussion's been 2-dimensional. So what if you have a 3-dimensional ugliness, right? What if you have some solid that looks like that? Oh my gosh, that's this is a generic case, but this is horrifying. You've got to think about what kinds of planar slices do you get from this bent, this is a wiggling piece of Jell-O, right? And how do you slice that up? And it's unimaginable. I don't even know if I could deal with something that's that ugly, and figuring out how many different corners am I slicing through, and how many different times do I sideswipe a face, and it's horrifying. So it'd be really nice to be able to play a pullback argument if I could do that as being an image, and then pull back the integral on the wiggled piece of Jell-O into a nice stationary, well-behaved rectangular box. Wouldn't that be nice? Okay. And the argument is very, very similar. I'm not going to go through any details. I'm just going to give you an assertion of what that stretching factor is. It's still a pullback. We're still going to be looking at pieces of size in the ugly domain, volume in this case. I'm still going to want to know how much does that represent a stretching out of a little piece of volume there, and that stretching factor, how much G stretches out the little green piece of volume to give me the red piece of volume. That green piece of volume gets stretched out by a factor. That's my stretching factor. The stretching factor is, oddly, lucky break, still the absolute value of the determinant of the Jacobian matrix. It's just that now the Jacobian matrix is a 3x3 matrix. So lucky break happens to be morally the same. Okay, we'll talk later about why that's true, why it is that this is the stretching factor. We've got enough going on right now that I don't want to go into that, but we will talk about that at a later date. So quick example, again, if you have a change of variables function given to you, plug and chug. And compute the appropriate partials. Assemble your Jacobian. Take the determinant. Right? Okay. This is going to be a hard picture to draw, so I'm not even going to try to draw it, but suppose that my domain on which I'd like to use this change of variables function is the image of this box. Okay, so I'm going to take this change of variables function here, and I'm going to look at the image by way of that function of this box that I really like because it's a box and it has, constant bounds when you break that up as an iterated integral. Its image is the domain, though, on which I'm sort of responsible for doing an integral. I want to pull back the purple integral into the green domain for a green integral. How do I do that? And we follow the formula. This integral on that domain volume is stretching factor times the pullback volume. Okay, just from the formula. We computed that stretching factor on the previous page. How do I know that stretching factor is positive? What happened to my absolute values? You gotta play the game. Give me 2 seconds. Let me finish this thing here. How do we know that our stretching factor is positive? Well, here's a formula for our stretching factor, and it says right there, U is always at least 1, and it says right here, V is always at least 2, and it says right here, W is always at least 4. Wow, okay, so let's see, 1 times 2 times 4, so that, punch it up, that expression there is always at least 63, bare minimum. So it's definitely positive. So the absolute values go away. Everybody on board? Okay. Question, yes?
How do you, so when you're creating an integral,
yeah.
Under doing the, how come you have Z in front of the determinant?
How come I have what?
Z in front of the determinant.
Yeah. So this was the question that we were asked. This is what we're charged with to compute that integral. So that's a given integrand. Yep. Okay. Yeah. No worries. Yeah.
Will it always be that the stretching factor is like completely positive or completely negative?
No promises. If it were, sometimes positive, sometimes negative, then you'd have to flash back to, you remember how you deal with that in Calc 1 classes, right? And that is you'd have to break the domain up and do for what values of x is the integrand positive, and therefore I can throw away the absolute values. For what values of x is the argument inside of the absolute value negative, and therefore I have to stick a minus sign on there, and you have to do it with two separate integrals. I will say that without making any promises, I will say that making a problem where that would happen here would make a problem long and tedious, and I have various incentives when I'm writing an exam for how do I want you to spend your time? What am I really interested in testing, right? And so, no promises, but I'm not super interested in testing you on your ability to handle gory details, right? But nevertheless, that is how you'd handle that. Yeah. Okay. By the way, don't forget further, this z thing, what do we do with that z? How do I rewrite that in terms of u's and v's? Well, don't forget, z is given in your change of variables function, right? So it's right there. So don't forget the change of variables function tells you what to plug in for. Okay, so that z turns into that. So it's really the same. It's the same deal as the two-dimensional. It's just three-dimensional and harder to draw pictures. But okay, all right. Okay, you remember we had these symmetry theorems, and I made Riemann some arguments to justify the symmetry theorems, and I think that's fine, right? I just want to show you there is a way to think of change of variables as justifying it as well. There is a version of this in one dimension in single variable that you might have seen. Clever argument that you can use to prove the symmetry theorem in one dimension is to do a substitution. You make the substitution u equals negative x, and then effectively when you do that substitution, you're effectively doing a change of variables. You're effectively pulling back and carry through details. So this is really just that argument. So let's imagine that we have a situation where we have a domain that's symmetric, and the function is odd over that same line. You'll notice same line, right? And I'm going to show you how to argue that the integral has to be 0, and this is effectively how to prove that theorem from a change of variables point of view. So here you go. D is symmetric, so it is its own reflection. Okay. Now we're going to apply the change of variables formula. There's the change of variables formula. Now I'm going to appeal to your geometric intuition. When you do a reflection, the stretching factor is 1. When you that guy that you look at in the mirror, right? He's got the same volume you do. Reflections don't change volumes. Pretty satisfying appeal, I think. So that's why this is 1. Okay. Notice all that's happening here is we're doing a pullback, right? So we're pulling back from the image domain to the pullback domain, plugging in for the the outputs are the change of variables function of the inputs. And so that's straight up change of variables. And now let's invoke the fact that the function has odd symmetry. It has odd symmetry. Whoops, circled the wrong thing. There we go. It has odd symmetry, and therefore f at the reflected point is the negative of f at the original point. So you get that minus sign there. Altogether, you have that this integral is the negative of itself, and things that are the negatives of themselves are 0. So there's the argument. So I think that's lovely. It's a nice way to use change of variables to sort of an alternative to the Riemann sum argument we gave before. Okay, enough of that. Okay, so we're done with change of variables now. Of course, you're going to do a bunch of exercises on change of variables. It's good to give yourself a lot of practice because there's things to think about and versions to deal with, and so make sure to take those exercises seriously. Moving on now to polar coordinates. Reminder, we skipped all this initially. right? This is chapter 10 actually, and so why did I skip that long ago? I want to talk about polar coordinates in context of what we're going to do with polar coordinates, and just to give you a little bit of a preview, we're going to use the concept of polar coordinates as a change of variables function. Turns out, polar coordinates, thought of as a function, is one of the best change of variables functions out there. And it's useful super often. So that's also why I wanted to wait until after change of variables. I mean, the fact that this is an example of change of variables makes it nice to do it after change of variables, because then I can use this wonderful tool of change of variables to be able to deal with these kinds of questions. So anyway, that's why I reorder the topics like this. The book has its own choices. That's fine. I think it makes more sense to do it like this. So here we go. Polar coordinates. Rectangular coordinates, you will recall, is a way of describing where a point is in the plane. Now, you understand what x and y coordinates are. This goes way back. This is a middle school concept, right? So, ancient history. Polar coordinates, very importantly, it's not really quite true. It is not the case that for every point there is exactly one set of polar coordinates. It is true that for every point there is exactly one set of rectangular coordinates, not polar. So the coordinates word even is a little uncomfortable, but anyway, that's how people talk about it. So here's how I want us to think about it. I want to think of polar coordinates as a function. If you give me two numbers, r and theta, then what comes out is a point in the plane as follows. Given these numbers r and theta, whatever that r coordinate is, whatever that theta coordinate is, that tells you what direction to go. Whatever that r coordinate is, that tells you how far to go in that direction. And notice that that then gives you a point, which of course has x and y coordinates. Okay, so you give me an r and a theta, out comes an x and a y. And of course, it's not hard to do what are the x and y as functions of r and theta. We can look at this little triangle right here, and again, flash back to all your old trig. Remember that there's x, there's y, right? And you got a triangle. R is the hypotenuse, and trig tells you these formulas right here. Reminder: make sure you're good at trig. It doesn't go away. The world is full of circles. So, okay. All right. So this function here, this is our polar coordinates function. Again, a little bit of foreshadowing. It's going to be an awesome change of variables function, but for right now, we're just trying to understand polar coordinates. Therefore, we just want to understand, how do these r and theta kind of work, and get a little bit of sort of a feel for them. But so here we go with that. As I mentioned, polar coordinates are not unique. They just aren't. Right? You take this point here, for example. That point. Well, that has a unique x coordinate, and it has a unique y coordinate. End of story on that. But with polar coordinates, I can think of this as being in that direction having been defined by going around sort of that much, and therefore sort of this value of theta, perhaps. Right, but I can also think about that direction as having been defined by going around that much, namely that value of theta. And I could go around as many times as I want. I get a bunch of different values of theta, perfectly legitimate values of theta, that, when interpreted as a direction, point exactly the same direction. Right? So, which one is the theta? What is the polar coordinate? Well, there is no canonical answer to that. There's a bunch of different thetas. Polar coordinates are not unique. Awkwardly, you can also go the other way. So, for example, I can think of that as that direction. And in that direction, how far do I go this way? Well, I go, it's not visible. In that direction, I go a negative amount. Right? So I can just think of it as negative values of r for a completely different set of angles. So polar coordinates, wildly not unique. Okay. Beware of ambiguities. You look at something like this, and there's a strong temptation to say, pi over 6. Pi over 6. We do pi over 6 all the time with angles. That must be an angle. This must be an r comma theta, because that pi over 6 gotta be an angle. And then you think, okay, it's gotta be an angle, and therefore there's the rectangular coordinates. But here's the thing. Believe it or not, pi over 6 is also a number. That could just as well be a y-coordinate, and this 1 here could just as well be an x-coordinate. This is an actual location. Right? So, heads up. Right? When you see something like this, you've got to really think through about, where did this come from? What are these things actually representing before you just, make an assumption about it. Okay, and I'm out of time, so we'll pick up here next time. See y'all later. Have a great weekend.